Hey there, math peeps. Today we get to talk about tessellations. Tessellations are very, very exciting. That's why I'm happy I get to do this with you guys. So, often we're in math class and we get that dreaded question. Have you ever wondered, when are we ever going to use this? I don't know if I ever have, but maybe you have. If you've ever had an awesome teacher like Mrs. Peters, she will show you how what you learn in math class applies to everyday life. Today, we get to do something cool because she let me teach you guys about tessellations. Here's some examples. Tessellations are everywhere. They show up in nature in items such as honeycomb, pineapples, pine cones, scales on fish and snakes, and many other places. Look at all those shapes in that honeycomb behind the words there. Isn't that wonderful? They also show up in architecture, such as in bricks, roads, windows, skyscrapers, places of worship even. They even show up in artwork. And they show up in mosaics, pensive pieces, optical illusions. The most famous artist who made tessellations was M.C. Escher. He focused on drawings that seemed ordinary, yet with a closer look became utterly remarkable. He created several impossible shapes, transforming images, and tessellations which intrigue millions of people even today. So those are examples where we see them. What are they? So if tessellations are all around us, man, we should really define what they are. Without getting too mathy, at least at first, a tessellation is a pattern which is created by a shape that when repeated creates no gaps, so there's no holes in between the shapes, no overlaps, and it completely covers a surface in all directions. Alright, time to get a little bit mathy. So we're going to talk about the math behind it. In order to create a tessellation which covers a surface with a regular shape, we should consider the places where these shapes come together. So they can come together at either edges or corners. Keep in mind that for both edges and corners, there can be no overlaps and no gaps. So first we're going to take a look at the corners. So again, our goal, no overlap and no gaps. So first we'll take a look at the interior angle sum theorem. Most of us know that the angles in the interior angle of a triangle add up to 180 degrees. Some of us may even know that the angles in an interior quadrilateral add up to 360. The sum of the interior angles of a pentagon always add up to 540. So here we have those out here for you, and I even added another column to show you a pattern. So notice it's 1 times 180, 2 times 180, 3 times 180. So those are counting numbers. But if we take a look at how those 1, 2, and 3 relate back to the number of sides, it's always 2 less than the number of sides. If we take the number of sides and subtract 2, and then multiply it by 180, that will give us the interior angle sum. So for 6, we get 4 times 180. And for any number, let's choose n to stand for any number, we get n minus 2 times 180. The interior angle sum theorem states that for any polygon with n sides, the number of interior angles is equal to n minus 2 times 180. If we want to look at a regular polygon to tessellate the plane, we simply divide the sum of the interior angles by the number of interior angles to find the measure of one of that polygon's angles. So if we want it to tessellate a plane, it has to also be a factor of 360. So here we have the number of sides is 3, so a triangle. The sum is going to be 180. The angle measured then, when we divide by 3, is 60. Is that a factor of 360? It sure is. Let's take a look at 4. So again, 4 minus 2 times 180 is 360. 360 divided by 4 is 90. Does that